a bunch of people already posted some questions, but you can go to slide.go, and F443 is the event. So you can post, and then you can upload the existing questions. I have some questions, and I already see bunch of interesting other questions were added. So we'll combine both of them. Okay, so we'll get started. Everybody who wanted to come here is already here. So I'm very pleased to have Dietterich here. I wanted to say a couple of things about how long I've known him, known of him, actually. So this is the handbook of artificial intelligence. It's very soon, it's going to be sold on Saltbase, because I think I and we are the only ones with copies of it. It was at one point of time, when I was a grad student, there were 3 volumes of this that Ed Feigenbaum actually was in charge of making. And the 3rd volume winds up having learning and inductive inference, which is an entire section, large numbers of things. And you will see, if you come close, that I have written lots and lots of penciled comments on that. And the entire chapter of that was written by Rao Kambhampati, who was a grad student, I believe, at that time at Stanford. So I grew up in my PhD reading about the work that he has done, and I think he probably has forgotten, but I still remember he interviewed me for my very first interview for faculty position in Oregon State University. And then of course, he's been a great stellar researcher in machine learning. Many of you know of that. Basically, in addition to doing top work in machine learning, he's also been like a great leader in the AI community. He was like the president of IMLS, the Machine Learning Society. He also started as the president of AAAI. He's a bit of a sucker for any work that needs to be done. He's also, I believe, in charge of the archive machine learning section, which is the sleepiest section. There's very little work that he agreed to do at some point of time. And now he spends time, basically, when you submit to archive, somebody has to click saying, yeah, this is not some plagiarized class project being resubmitted. So he is one of the people who actually helps with that. And then of course he was the AAAI president, as I mentioned. And more recently, he says he's emeritus. I don't quite understand how that works, because he's all the time working, he's all the time writing papers, as well as making very, very thoughtful comments about the AI craze, AI hype, AI controversies, etc. On Twitter, I don't know how many of you follow him. Very, very, he's one of the few people I follow, and I always know what he's saying. It's like a very thoughtful, even thing. So when he's coming here, we couldn't quite make it happen that he could give his research talk, but I still wanted you guys to hear some of his general thoughts on AI, and so that's what we're going to try and do, and we'll see how that works. Let's see. So let me ask a few questions I have, and a few questions you are asking. So I guess, when I first joined, and I'm sure when he joined too, if you say there's an AI talk, nobody will show up. Now, basically, we have to kind of put barricades to stop people from showing up. And part of this has been with deep learning thing. So I'll really start by asking Tom, who's been in machine learning for quite a long time. So sort of how were you surprised about the deep learning wave in what ways? Was it surprising to you, given how long you know the work that was going on behind it? And also sort of how far do you think it might go?
Well, yes, I was surprised. I was just looking there because if you look at that learning inductive inference chapter, you really would not recognize most of it as being machine learning. It was written sort of before we discovered that statistics had something to tell us about machine learning. When I was a graduate student at Stanford, I was about 100 meters away from the statistics department, And in the stat department, Trevor Hasty was a PhD student.
Oh, okay.
Rob Kambhampati was a PhD student. We never met, and I think even if we had met, we wouldn't have thought that we had anything to say to each other. But 10 years later, by 1990, I mean, the PDP book had been out, and well, support vector machines hadn't been invented yet, but certainly decision tree methods had become very powerful, and rule learning and stuff. So, and in particular, the formalism of pack learning that we wanted to have, that it was okay to be approximately correct. We didn't have to actually get exactly the concept that the teacher had in mind.
It was impossible to get it.
Well,
exactly
we were having a very hard time, yeah, it was definitely.
Yeah.
But, and so when the, I guess it's now known as the second wave of neural networks back in the 80s and 90s, when the PDP book was published, you know, I got interested in neural networks and experimented with them. But they were very frustrating to use. I mean, I thought the thing that I thought was most interesting about them was that it was sort of like a new kind of modeling play. You could design the shape of your neural network to do all kinds of interesting things. So it was much more flexible in some sense than rule learning and tree learning. You could learn about relations in certain strange ways and you know, do sequences. And so it was a very flexible thing, but it was also extremely hard to get it to work and very slow. You know, I invested in one of those neurocomputers. It was called the Synapse, sometime in the early mid-90s. I don't know. Its big claim to fame was that it could learn net talk in 6 minutes or something instead of 2 hours on an ordinary machine. It was a fixed point precision neural processor specifically for background.
Okay.
So I feel like, you know, it's seeing this wave. It's kind of a repeat of that. Now there must be 100 startups doing specialized hardware for deep nets. But I remember toward the end of the 90s, right, people moved to teaching support vector machines in class because, as one colleague said, you know, when I assign a neural network project in my class, only about 10% of the students can get it to work. And when I assign a support vector machine, 90% of the students can get it to work, and they all get the same answer. Because it's a convex problem.
Yeah.
And that was just so well behaved and wonderful. And so I think that's why support vector machines kind of took over as the dominant thing. I mean, there was also obviously random forests and boosted trees continue to be very successful here. But you know, you had good control over fitting. You know, you really couldn't interpret them with kernels, but they were very flexible. And so, yeah, all through the 2000s, then I had a project in computer vision for recognizing insects living in freshwater streams. Sort of an ecology project. We were using David Lowe's SIFT features and bags of SIFT then going into a SVM classifier. And it worked pretty well for us. But then, of course, in 2012, we had the Krzyzewski paper that just you know, really cleaned up in computer image learning. And so, so the question is, how far can it go? I don't know. I mean, you know, my inclination is that I think it's an interesting research program to push it as far as it can go and see where it fails. And this is where I've had big debates with Gary Marcus, because Gary, you know, has lots of good critiques about things that seem to be that the current deep learning techniques really are not doing. And of course, we also have all this work on adversarial behavior, the brittleness that we're seeing, and also it seems that our bag of tricks for controlling overfitting don't seem to translate. So so putting weight decay on the weights of a deep network doesn't really seem to do anything. I mean, people do it, but stochastic gradient descent by itself, especially combined with you know, batch norm, seems to automatically attenuate the learning rates and prevent overfitting. And although you can, you know, as those experiments show where you randomly label things, you can drive it to overfit, but you have to work pretty hard. Now, back in the 90s, we also noticed that it was really hard to get neural networks to overfit. But I always figured that was just because we would lose patience. It takes so long, it was overfitting or underfitting by early stopping, right? You just after running it for 3 days, you'd say, well, it doesn't seem to be making much progress, so we'll stop it here. And people did cross-validate the stopping point if they were really trying to tune out the last fraction of a percentage point of improvement. But overfitting wasn't a problem there either. And so, I think that is still a big mystery, what's going on there in terms of overfitting control. Because, and so I'm, I'd say deep learning is full of mysteries. Because, as you see, one thing that was really, usually in machine learning, experimental work is way ahead of theoretical work. And that's certainly true right now. We have all these experimental successes, and we have a huge gap between what we thought we understood theoretically and what seems to really be happening, right? And the exception really would be support vector machines, which somehow, sprung out of the brains of the gang at Bell Labs.
So Vapnik says.
Well, Vapnik wasn't really the guy, but his students.
Yeah.
Isabelle Guyon, I think,
Yeah.
and her husband really were the ones that made it work. And they actually, I was talking to Isabelle at NeurIPS about this, because I was saying I thought it was a combination of ideas that were out there, because at Wisconsin there was both the representative theorem, which had been proved by I can't remember her name now, in statistics for spline things, and then there was also a lot of work on using linear programming or quadratic programming to fit classifiers, but OBSR. And so they weren't talking to each other, I don't think. But Vapnik, or really Isabelle, but she said that she wasn't aware of that work actually at the time. But in any case, the ideas were out there, and she said that actually they were inspired by a footnote in Dude on Heart. I think it's still good. If you can get a hold of a copy of the original first edition of Dude on Heart, read that. The revised edition has all kinds of other stuff. It's not so important, but that first book is amazing. So I don't know how far they can go. Joshua and Jan in particular have this sort of research program of, let's see if we can do causality, let's see if we can do self-supervised, unsupervised representation learning and reasoning and all kinds of things. And I hope they succeed. On the other hand, as a sort of more old-fashioned AI guy who loves things like SMT solvers and SAT solvers and planners, we know that if we can move to these discrete combinatorial spaces, we have some very powerful tools there as well. And we understand abstraction and approximation there in some ways that are much harder, I think, to deal with in the continuous world. So I don't know what so I guess, if I was trying to build a big AI system today, of course it would be a hybrid system. And if you look at, I take the Google search engine, it's a giant hybrid system, or the IBM stuff, or just any system, any real system is a big hybrid. But that's kind of an engineering necessity. I don't know, could we have something that, a big problem when I was working on, so in the 2000s or so on, I worked on this project that SRI led called Kalo.
Yeah.
And that was, the goal there was to make a sort of intelligent...
That's sort of the progenitor of Siri.
Right, Siri was the main thing that sort of came out of that, in the sense that there's not a single line of code shared. But the team that built some of the things for Kalo then said, let's do it again as a startup company and do it right this time. And in some cases, it was like the third try at it. But one of the things that was a big problem there was you had all these different independent components being engineered by, there were 16 subcontractors all doing machine learning in that thing. My job was to manage them all and to try to tie them together and get these different components. But but there was no system-wide awareness. So you would have to teach your email classifier about a preference, and then you have to go over and also teach your document ranker, and then you might have to teach your calendar thing, and more or less teaching the same thing, but we didn't have any kind of I don't know, end-to-end or joint awareness or anything like that. And from what I understand inside Google, it's the same thing. I mean, the search engine is built out of all these components, but they sort of have to separately retrain each part. So I think there's huge issues at the systems level of AI, which is super hard for us to study in the university.
So one thing that I guess, I mean, you also sort of express sympathy for the viewpoint that you shouldn't be just looking at neural networks as basically doing good supervised learning. You should be thinking of, at least I mean, that you should be thinking of this whole thing as this differential programming and
Right.
and so do you have anything to say about how far that's even more open-ended as to how far it might go? Because I think, I mean, DeepMind, for example, has considered like, you know, simulating Turing machines, neural Turing machines,
Right.
and so on. And so do you think that would probably open up a lot more connections to reasoning?
Well, I mean, a couple of things that I'm very excited about. I love this idea of, let's make a differentiable physics engine and stick it in there. So I don't know if you've seen this work where they basically put a differentiable physics engine in there and then learned Pong like in just a few trials, because it turns out the dynamics of the balls in Pong is non-Newtonian. Even though you've got this physics engine that is Newtonian, basically you have a neural network in front of it and behind it, so you can sort of lie to the physics and then also correct, lie afterwards, or transform the answer afterwards. But it gets you sort of approximately the right behavior, and so it only takes very few trials then to do something interesting. So that's one thing, is that we can embed a lot of domain knowledge in the form of simulators that we can stick inside of this end-to-end differentiable framework. The other thing is, let's see, what was the other thing? Oh, the other thing I'm really excited about is probabilistic programming. So, I was involved in this, DARPA had this thing called PAML, Probabilistic Programming, Advancing Machine Learning. And there were a bunch of teams creating these probabilistic programming languages. But David Bly's group in particular, so a lot of these probabilistic programming systems, right, rely on using Hamiltonian Monte Carlo, right? So their reasoning engine is basically Monte Carlo sampling. But with Hamiltonian Monte Carlo, you use the derivatives of the likelihood or whatever to guide the particles that you're simulating. And so that turns out you can write all that as differentiable programs.
Yeah.
And so now there's this TensorFlow distributions, which is basically a combination of the Hamiltonian Monte Carlo, and also he has this I can't remember what it's called, general variational approach, black box variational.
Yeah, the one that Bly's group.
Yeah, those both came out of David Bly's group, basically. So I think that's super exciting because, I mean, I'm a big fan of probabilistic models because I know what the probabilities are alleged to mean anyway. And so I think that's really interesting too.
So I guess one of the interesting things I guess currently that's going on, and it was also related to one of the questions that people were asking, is so back in the day, even learning systems, there would be significant sort of hand coding of features. For example, there was this understanding. In fact, the earliest AI systems all involved sort of writing, what you know about the domain, so knowledge-based sort of a thing. Now it's become completely, especially for the perceptual tasks, it's become completely just learning from examples. And there have been some cases, at least you probably are aware of too, where I've seen taking a rule that somebody knows and converting it to a huge number of examples, because that's what learning systems will work with. So instead of going from data to knowledge, it's knowledge to data. So I think there have been some people interested in sort of background knowledge. How does background knowledge come into this sort of, especially the deep learning neural network stuff?
But in general, yeah.
I mean, for conv nets, for example, the best they could have said, they seem to be saying is, special types of architectures, inductive bias in architectures. I know you have talked a lot for a long time about sort of widening the pipeline between that. So do you think of better directions than just sort of hacking different architectures? I mean, there are cases where obviously I know how to do part of the problem, and I would like to be able to tell this to the system rather than sort of give a huge number of examples. So I was wondering.
Yeah, but it does seem that, that there's we don't have a good API for saying, well, I know this something and I want to impose it on the learning system. And this is true with or without deep learning. I mean, if you just think about decision tree learning or boosted trees or something. Now, one reason to be skeptical is that often our knowledge isn't very good. And when we either simulate from it to create, to do data augmentation, or when we impose it as a constraint, we don't necessarily get good results. And so, I mean, I would say that the computer vision community in particular, right? The transfer from, or the starting point of having SIFT features and also HOG features, which were very carefully engineered, clever things. There's a lot of signal processing knowledge behind them about image statistics and so on. But it turned out that letting the system learn its own intermediate representation was hugely better. And so that's this really depressing, this interesting result that I think that we're really worried that if we code knowledge in there and it's not correct, that we'll just handicap our systems. On the other hand, it seems to me that we have a desperate need to get knowledge into these systems because I was joking with Gary Marcus a couple weeks ago that we seem to have solved the expressiveness problem. Deep learning gives us very, very expressive model classes. But of course, we haven't solved the sample size problem. So we've got wonderful things that can express really good classifiers in them, but it takes us millions of examples to then find those good classifiers. And so that's holding us back hugely. I mean, whether it's just working domains like medicine where you don't have millions of examples, or where you want to do transfer learning, or one-shot learning, or all these things where you have very tiny sample sizes, non-stationarity, which gives you small sample sizes. We can't really do deep learning in those things without lots of hacking. So we know we need domain knowledge. Okay, the question is, what form should it take? I mean, so with the physics engines, that gives us one way to do it. And there's some similar stuff in chemistry. There's some other weird things. But right now, the main API we have is generating pseudo data from.
Yeah, that's
and then because we know the learning algorithm will listen to training data. So, but we don't get any guarantees out of that. Or at least I don't know. I mean, maybe there is a way.
I think at some level, I guess, if there's a way of converting everything into data, then
we can brute force our
language thing. But it seems like they must be
planet
better. And then the other connected version is, I mean, you pointed out that oftentimes our knowledge is not completely correct. That also, I think, changes from like class of domains to class of domains. I mean, especially perception, we have really bad knowledge. I mean, I think SIFT and HOG features, and I keep thinking that vision is no longer a field as far as I'm concerned. It's just machine learning.
There's tons of things.
Yeah.
Maybe it's a part of it, but it's still a huge number of problems.
Yeah. So I mean, I think it's like partly because there wasn't much to give, but there are enough other domains where people have, at least they have standard ways of doing things, and that might not be the best way of doing things in an optimal world, but starting from that should still be a useful. So.
Right.
Interesting. So actually, I think it's related to that, I guess, is this aspect of if systems are learning basically representations from the data, it obviously has more direct conflict between the learned representations of the system and the representations that people might actually have.
Which is another reason we have this mismatch.
Exactly. So it's become like the whole explainability, interpretability aspect. So I think, do you see that as something that we just have to live with? And I mean, so what are some of the what are the ideas?
Well, I feel it is absolutely a core problem we're facing right now. Even if we just wanted explanations, we need to make that vocabulary jump from whatever's happening inside the network to human understandable concepts, right? And so this is coming up in our work on explainable AI, right? Prasad Tadapalli has this interactive naming effort, which is just one way of trying to elicit training data from people about attributes. If we want to describe the, I worry a lot about safety and reliability, robustness problems, and there you want to communicate to the human user when the system is trustworthy and when it isn't. And you need a vocabulary for that. And so again, we start to say, well, we need to teach it, train up classifiers for all these human understandable concepts, and then use those to interpret what's going on inside the network. And there's this work on network dissection, which is more or less the same thing, trying to find neural network activations inside a network that are correlated with human understandable concepts. I've heard work here today working on this too. So it just seems to be, we're finding this problem everywhere. So maybe we should just accept the fact that we're going to have to not only teach the system the overall task, but we also have to teach it all the concepts, the whole vocabulary, and
so you can do the thinking in whichever way, but you need to provide some
But that certainly would then of course the interesting thing is, can we correct the system in that vocabulary, right? I mean, we've done some work at Oregon State, actually we were using, I think, just naive Bayes classifiers or something like that, but particularly my colleague Margaret Burnett and Wenqing Wang, so she's an HCI, right, and I was collaborating with her too, and we were trying to figure out how we could get user input usefully back into a machine learning system. We looked at email classification as our domain, and so we would explain why we had classified this email message as being in category X in terms of sort of feature importance. And then we gave the user the ability to, like with sliders, change that feature importance and give them feedback about, oh, if you did that, that would cause us to make these mistakes over here, but we would get these points right, and so on. So we gave them a kind of user interface where they could essentially be the learning algorithm. But in some sense, it had the flavor of, here's an explanation, now correct us in that explanation, and then we're going to try to go and fix what the real learning algorithm, the real learned concept, so that the new explanation would match your correction, right? So there could be a faithfulness mismatch between the explanation we give them and what's really going on, but we could still try to use that as a communications medium. And so we had some success there, but basically we had to use extremely simple learning algorithms, right? But basically some sort of local linear or local naive Bayes type classifier in order to make it really transparent to the user. And maybe that's part of the solution. Of course, we've had some discussion here with some of you today about, maybe we shouldn't use deep convnets or resnets. Maybe we should use things that are more like metric learning or some sort of, or clusters in latent space, or where we have a more understandable classifier, and maybe we can explain what the features or the dimensions of that latent space, or GANs that we can control because we have vocabulary and the sliders, we know what they're doing. So
I think there's like a trade-off between understandability and performance in some cases.
It seems like right now, of course, we talked to Cynthia Rudin, she was saying, no, there isn't, we should be able to do it. And more power to her. I mean, if there's somebody in the world who's going to figure out how to avoid that trade-off, she is probably it.
So at AAAI last week, Kasparov was saying something to the effect that something that many of us know, and of course you have also said, that in any closed system, machines will eventually triumph over humans. That in some sense, it's actually easy to outperform humans in closed systems, and that's sort of the Achilles heel of AI systems has been these open world systems. I mean, your essential address was about robustness and so on. So I was
and yours too.
Yeah. So I was wondering, what do you say? So what do you think? What do you see as like some of the best, most promising approaches right now towards that? Making systems more robust, AI systems more robust.
Well, you know, I mean, in my presidential address, I talked about basically adversarial strategies, right? So if I want to, there is you know, some good theoretical evidence that suggests that right, that if we train our systems to be robust in the sense of, say, robustness against an adversary, but that also confers robustness against things like model misspecification and incorrect learning of our models. So in my talk, I quoted a lot of the work of Menor, who comes out of the robust optimization world, in sort of, which is more an OR, right? Where in operations research, you might have a linear program that you've elicited by talking to experts or whatever, but you might suspect that maybe the linear program isn't actually the real linear program. Maybe there are errors in your elicitation about the coefficients in the objective function or the constraints. And so you imagine that there's an adversary that's allowed to actually mutate your LP into a different LP, and you want to come up with a solution that works well against that adversary. You give that adversary a budget so they can't do arbitrary things. And basically, the great thing about linear programs is that if the adversary can only make convex changes, then it's still a convex problem, and you can still solve it. And if it's actually convex polytope changes, then it's still an LP. And so it's LPs all the way down. With deep neural nets, we have now, there's of course adversarial training. But we're usually, we have a limited adversary because we don't know what the right adversary is, and so we're competing against an L2 adversary, an L1 adversary, or something. They just can perturb things within a ball. I mean, this obviously helps, but somehow we don't think that's the right geometry, right? I suspect. I mean, yeah. So I think, but the general strategy is to say, okay, let's make a system that's robust against an adversary who's allowed to make some kind of tweaks or attacks on our solution, and we still want to have a strong solution. So
I think a related question, I think, is something that's also clear to your heart, is most often right now these systems that are possibly brittle are already being used in practice in quote-unquote human organizations with these machines, these systems and so on. So you sort of have been talking about this robust human organizations, and so what's the takeaway that you want people to do?
Well, so I've been doing a little bit of reading in this literature that was from the 80s and the 90s about how human organizations managed to be robust in the face of uncertainty and failures in their processes and procedures, right? So there's a group of organizational psychologists at Berkeley in the 80s and 90s who studied what they called high reliability organizations, or HROs. And they describe 5 properties or practices that these organizations have, which I can tell you about in a moment. But my motivation is to say, well, if we want AI systems to be robust, maybe we should try to figure out how they could do these 5 things. And also, if we come, as we often do as technologists, and we say, into an existing robust organization, and we give them a tool that's supposed to help them, how do we avoid damaging their robustness? You know, how can the AI tools support robust organizations rather than destroying them? And so the 5 practices are: number 1, there's a subgroup who's responsible for maintaining situational awareness at all times. So the kinds of things they were looking at were things like nuclear power plant operations, air traffic control, surgery, hospital surgeries. And so there's some people whose job is just to keep track of everything that's happening, the locations of all the planes, or the state of the plant, or whatever. Then there's a deep prior belief among the entire team that their system has unknown failure modes. So they don't believe that they have complete mastery of the system, but they believe that there are unknown failure modes, and one of their goals as an organization is to discover those and come up with ways to deal with them. And how do you discover unknown failure modes? Well, of course, you can have failures, and then you find them out. But they look for anomalies and near misses. And so, I think there's a tendency in a lot of organizations that if something unusual happens, but it doesn't actually lead to a failure, you say, well, it's just random noise or something. But that's not the attitude of these organizations. These organizations say that anomalies and near misses are the only evidence we can have about potential future failures. So each of these we should study in detail, ideally with a very diverse team that can come up with many, many hypotheses for what caused the anomaly or why this near miss occurred. And then brainstorm possible fixes, which may involve sort of thinking outside the box of their current formulation. So they call this improvisational problem solving in this literature. And they claim that these teams are able to practice improvisational problem solving so that when they're in the midst of a crisis, they can quickly come up with a repair or a patch to work around this new failure. And then the fifth principle is that the person in the organization who has the most expertise about the specific failure should make the final decision. And that's the idea of empowering even the people who are low in the status hierarchy. So this has been the big thing in hospitals, right? Is that the nurse the lowly nurse in the operating room should be able to halt a surgery if he or she sees a problem. Whereas the surgeon is treated as God, but no, these teams are trained that everyone has a responsibility to call halt, and you can do that without any repercussions. And similarly, there's another wonderful euphemism called cockpit resource management, another CRM. It's very confusing to me, but for those of you who are customer relationship management. But this is a euphemism for teaching co-pilots skills to be able to break into the pilot's tunnel vision when there's some problem with them. Because there have been several airplane crashes that have occurred because the pilot got fixated on some sub-problem and lost overall situational awareness, and is not hearing alarms going off, is not hearing the co-pilot saying, there's this mountain here we're going to crash into. And so basically these teams practice intervening in high-stress situations. So anyway, so that's the 5 HR principles. So what can we do in AI? Well, we can do situational awareness actually really well. Although I think the human teams need to have situational awareness about what version of the AI system they're running. When was it last updated? Was it just retrained last night and therefore it's like potentially buggy? But then, and then there's the anomaly detection, and so I've been doing a lot of work on research on anomaly detection. But near misses, I think the only mention of near misses is like Pat Winston's thesis or something, right? But I think it's interesting to think about this like in the planning or reinforcement learning setting. Say you followed a trajectory to the goal. Now, you should do some sort of, in hindsight, what were threats to my success? That if something had just gone slightly differently, I would have failed. Because that's, like sensitivity analysis that takes into account the reward and function to say, this is a serious near miss. And from that, do I need to change my policy? Do I need to change my sensing? Or, what do I need to do to avoid that near miss in the future? I think there's very interesting research there. Improvisational problem solving. When I looked over the AI literature, aside from jazz improvisation, the only thing I saw was mixed initiative planning.
Yeah.
And I think that we need to revive that field and get
Well,
more people
we're doing it slightly differently, except previously mixed initiative planning involved humans going into the planner mode. Now it's opposite, planners coming into the human mode.
But either way, how can the AI system support humans doing improvisational problem solving? And if it was a totally autonomous AI system, what would it mean for an AI system itself to do improvisational problem solving? How could it get outside of its box? Could there's a bigger box? Can we have like fallback boxes that with larger? I don't know. I think this is a fundamental deep question in AI. How do we escape from our ontology to a bigger ontology? And then the trusting the person who has the expertise. I think that mostly comes up in the context of human-machine systems. Because of course when we look at the AI plus human system, then let's say the AI system is doing a lot of situational awareness, but it needs to achieve a shared mental model with the humans. so that they also have that situational awareness. And similarly, when the AI system detects some anomaly, like my anomaly detectors might be like some of the things we were discussing today. You've got an autoencoder with a reconstruction error or some weird thing. How do you turn that into human understandable? How do you explain the anomaly to the humans? Yeah, I mean, it's the same problem except worse, I think, than even in the supervised learning case. And then, of course, reasoning about, helping the humans reason about what might be causing the thing, how can we work together with them, and then the final decision, making changes and all that stuff. It requires this, theory of mind and, well, all the things you're doing. So I think when I think about the AI plus humans, you here are probably doing the best work that's out there at looking at this. And so,
I didn't pay for this.
I tell everybody, this is the, pay attention to what's going on here because.
So one of the things, so there's some questions that students asked on Slido that rose up in voting, so I'm going to ask a few of those. One of these is, it's interesting for some of the students, I guess, listening to you, hearing all these other things other than just deep learning and number of layers, right? Essentially, so you talked about psychology, you talked about OR, you talked about regret minimization, you talked about, so the question is there anything else other than just machine learning? And what sort of, if you look at something like the Intro to AI course, the Navics, etc.
Right.
So some of the people who are coming into the area are basically just, pretty much, I taught Intro to AI last year. Everybody knows supervised learning, at least they think they do, and everybody knows how to start TensorFlow, they think they do, and that's about it, So the question is, some of the students here are wondering whether that's enough or whether they have to do something more. And so I guess, presumably, I guess to some extent you answered a lot of it, but I was just, what do you say in terms of, so another, actually a typical way somebody put it is, if everything can eventually be learned, then is there any need for any other areas, like the reasoning, the communication, the coordination aspects, and so on? So what's your, it's also more of a mentoring question. Should people just be looking at, how many layers to add and see what happens?
Well, on that score, I'll tell you a story from my past. So in 1991, I was working on sabbatical at Berkeley and working at a startup pharmaceutical company. We were trying to use machine learning to drug design, and basically that failed. But Daphne Kohler now has a company, and there's a bunch of really exciting work happening actually using GANs to generate molecules and to do optimization in the latent space of GANs. It's very, very interesting work. I don't know about her work specifically, but I see a lot of papers come through arXiv because actually in arXiv we don't have a good category for this, so they're always an exception handling on this. So I was in a meeting with a few people, and we were trying to figure out our algorithm wasn't working, and we were just imagining all these tweaks. And Tomás Lozano Pérez was also involved in this company. And for those of you who don't know, he's expert in sort of robotics and
configuration space.
But configuration space and just reasoning about kinematics. And of course, he was sort of, he had gotten bored with robotics conferences because he said, I can predict 90% of what each speaker is going to talk about. So he decided to branch out into molecules, which are just like really complicated robot arms anyway. Anyway, he stuck his head in the door and he said, it sounds like you guys are searching the space of Turing machines. There's an awful lot of them. And that's my reaction to all of this, neural architecture research and playing around with do I need more layers or wider or this or change the transfer function or whatever. That's a huge space. I don't know how many years you plan to be a graduate student, but I think as T approaches infinity, you might graduate. So I think that, and what he said was, you need some principles. And I think the machine learning field as a whole, it's, to come back to my previous theme, obviously experimental work has gotten way ahead of theory. But now we're seeing a lot more good work in the conferences that are really trying to understand what is exactly going on, right? Is the, how close are we really to just lottery tickets? Is our optimization just shutting off ReLUs that are not doing anything good? Or are we really, I mean, what's really going on in this stochastic gradient descent? And you know, do we have these non-robust versus robust features? And how could we ignore the non-robust ones? And I think, and what's the story with this double descent phenomenon?
Yeah, that's really
So, you know, the pattern recognition people, you know, back at least the last time I paid close attention, if you read Dude on Heart, right, they'll talk about linear discriminant analysis and quadratic discriminant analysis, right? And this is where you assume if you're, that you can model the classes as Gaussian distributions. And then you either assume that they share the covariance matrix, in which case the optimal separator is linear, or they don't share the covariance matrix, in which case the optimal separator is quadratic. And in that field, they discovered this phenomenon they call the peaking phenomenon, which is that when the number of training examples matches the dimensionality of the model, the error rate would shoot up, and then it would fall again. So they also saw this double descent phenomenon in those days. And so I think that we're just rediscovering something that they've already known about over-parameterized systems. But they studied it in a linear case, and maybe we should go back and read that theory. Because, you know, one of the other strong heuristics for doing research in machine learning that Jerry Friedman, you know, when the statisticians started coming to machine learning conferences, they would say, well, have you looked at this in the linear case? Because usually that tells you a lot. Before you go all this nonlinear nonsense, you know, can you reproduce this phenomenon in the linear case, and maybe you can understand it there. And so I think that we need more of that. Okay, but in the large scale, I mean, I feel like, so I feel like with deep learning we have solved the expressiveness problem, but we have not solved the representation problem. And I really wonder if we're learning representations, right? If the lottery ticket hypothesis is true, we're randomly generating them, and then they're good enough, and we just have to figure out which one to use. So, you know, more and more as we dig into this stuff with explainable AI, and I was just telling you about Alan Fern's results on you know, Palm turning out to learn basically an open loop controller that doesn't even look at the screen. And we've got to really ask, what are we really learning in these systems? And we may be shocked that we're not learning that much. Or maybe we won't be shocked because we're seeing how brittle they are, so that suggests that maybe we're not learning what we should be learning. Yeah, I don't know. I think we're in desperate need of good scientific, hypothesis-driven experiments in machine learning and more theory-driven work in machine learning right now.
So there was a related question. What do you think?
But can we do it all with learning?
Yeah.
Well, as a machine learning guy, my reflexive answer is, if you can't do it with learning, you don't really understand. And I even said this in a tweet, almost immediately regretful. You know? I was like, oh, should I delete that? Because I started to think about...
Sorry.
Well, and because I would have to say that I'm personally having a little sort of Kuhnian crisis right now, right? Because that has always been, I mean, back in 1980, I had to argue really hard to do a thesis in machine learning.
Yes.
Because Ed Feigenbaum said, statistical learning, that's never going to get us anywhere. You should reformulate it as knowledge acquisition. It's all about getting human knowledge into the computer. And so work on that. But it turned out, you know, that we're winning or whatever. That's the work. It's wrong to even formulate it as a battle. But I guess we're seeing that there are lots of things where maybe in principle we could learn it, but maybe in principle means completely infeasible sample sizes. So in particular, I've been very interested in the problem of open category or out of distribution learning, right? And so in the open category case, your training data was over K categories, but it turns out there's 2K real categories out there, and in your test data, you're going to get queries that are kangaroos and walruses and just stuff you never saw in the training data. And if there's a penalty for getting those wrong, then you better not. So the trouble is that there's often what is known as nuisance novelty in images our training data, so something will be new, but it's like in the background, or it's like kind of incidental to the task, but we never saw it in training, and the alarm goes off and says, well, reconstruction error is high or whatever. I'm surprised by this image. How do we tell the system that this is novelty we don't care about, right? I mean, the old machine learning answer would be, well, you just need more data, exercising all the ways that there could be variation, so the system learns that that's normal variation, and so it can ignore it. But that's not really a satisfactory answer. I just don't think that there's that much data in the universe to exercise all of the ways that we could have variability. Whereas if we have maybe some domain knowledge, it says, well, yeah, things can vary in this dimension, and I do not care about this. This is an unimportant dimension of variation. Or we were having all these other discussions about what about these undersampled groups? You know, especially if you're working in medicine or some other things where data is expensive and it's private and legally protected. And so you can't just ask for 1 million examples. Plus, it's also maybe not very stationary. And so there's an inherent rate limitation on how much data you can get. We need some way of communicating what are the dimensions of variation where we are undersampling and make sure we protect those and we don't lose them. And we're seeing all kinds of stuff popping up in supervised learning, in calibration in my case, in generative models, which I heard about today, where the machine learning is really good at the common case, loves those big, the typical set, and just throws everything else away and says, oh, that's just exceptions, that's noise. I didn't have to get that right? In learning theory, said I only have to be probably approximately correct, so I'll be approximately correct except for white males.
So a related question that people had, I think you sort of mentioned, touched on it several times, what are some of the most underrated ideas in AI that you think right now that people should focus more on? I think you said some things, but maybe you have other type of things.
Well, I mean,
areas that need more effort as against just the ones that
well, it's obviously something in machine learning, but if we get outside of machine learning, I would think, human-machine interaction, and obviously I'm speaking to big, strong advocates of this, but of course there are many people in AI and machine learning that are realizing that, well, for one thing, for years we were working on this stuff, but nobody was using it, and so we didn't have to worry about users. But now, so they're starting to deploy this stuff, and suddenly we're having a need to look at the whole interface, and as I say, support. We're really trying to make humans more effective, or create, these symbiotic interactions between humans and machines. And so we need a lot more attention to human-computer interaction. We're all doing human subject studies now. We need to build our skill set there and learn about review boards and all the ethics of those things. And so that's a big thing. Another one I think is the theory of measurement. So, right, if you ask a machine learning person, where does this data come from? They give you a URL. But the question is really, how is it measured and how is it labeled, right? And this really, I had really not encountered this until I started working on ecology problems, right? But if you're interested, as ecologists often are, in understanding, like estimating the size of a population, estimating the number of species, or trying to understand the habitat requirements and preferences of a species, you send human observers out to go do species counts. And so you might be, if you're a bird watcher, you're out there reporting on birds. But you will have a certain detection probability. You will fail to detect a lot of things that are out there. And so if you look at the raw data counts, you don't know how to interpret them. They call this zero-inflated data because there's lots of zeros, which was not failures to detect, that are truly non-zero, so they're false zeros. And so so you actually have an observation model that says when the observer goes out there, there's some features about like if it's birds, it might be, well, I'm in a thick forest, it's maybe it's windy, and so the birds are hiding. Maybe it's breeding season, so they're actually displaying more observable, and so on. So there are these features that determine your detection probability. You need to model those. You need to learn that model as well as learning your model about the species distribution. And so you end up having two models, and the true observations are hidden. The true presence or absence of the species is a latent variable. And we're just not used to thinking about that very carefully. But the same thing if you get into preferences, obviously, where the preferences or the values or the whatever are all latent variables. We try to infer them from the observable behavior of people, obviously their beliefs and goals, all that stuff. And in medicine, of course, we have all these other things, right? I mean, Rich Carwin gives his, hospital readmission thing with for pneumonia patients, right? Where, what he looked at a bunch of data on patients with pneumonia in Pittsburgh hospitals, and it turned out that patients that had asthma had a higher probability of recovery and lower risk than patients without asthma. And we know causally this is totally wrong. But what was really going on was patients with asthma were treated much more aggressively, much earlier, and so they were getting better care. Okay, so that's again, now you're actually observing a policy being executed, and your data is only generated by this policy. It's not a random objective sample. And it turns out that's basically universally true, right? There's always some process that's generating your data, and it's rarely a random sample from the population of interest. So we need to put that into our models. And of course, this is a case where we could try using a deep net with some latent layer, but I think it would be much better building a probabilistic model with latent variables whose semantics we know what we want them to mean, and then we can ask identifiability questions. From this data, can we actually identify those parameters or not, uniquely? And if we can't, then we know that we can't enforce the semantics that we're hoping on those. So I think all this, and this is a lot of what Pearl also talks about, is with his causal models. Can you really identify this causal effect or not? And he can tell you. So I think this is another thing. Statisticians talk a lot about the identifiability of parameters. In machine learning, we always say, we don't care about that. We're just making predictions. It doesn't matter if we have 10 times as many parameters as we know as we need, because we don't care about their semantics. Well, now we care about their semantics for a whole raft of reasons, and so we need to. And that's why I would favor probabilistic models where we have some idea of the mean. Maybe we need some, again, at perceptual level, maybe we need some deep learning stuff, but yeah.
So one thing that's sort of related to some of the things that you said is, like you mentioned earlier that, previously people weren't using our system, so we didn't have to worry about a whole bunch of things. And one whole host of problems that became pretty, very important now is this societal impacts of AI technologies, this whole issue of, I think pretty much everybody is an expert and saying the AI systems are biased, somehow we have to do this, that. And so what do you make of this whole concerns? You mentioned some of this already. What do you make of the general trend there? And also, how much is causality and causal learning can possibly come to a rescue for sort of handling this in a technical sense against?
Well, I don't know how far we can go with causality. I don't feel like I'm an expert in it. I've read the Book of Why. I've read some of the other older causality books. I've read some of Shokop's work, but I don't feel like we have a unified sort of approach to causality. And I've been sort of. Pearl's always yelling on Facebook about how learning, you can't go from statistical level to the causal level. And I say, yeah, but what if your hypothesis space is the causal space, then what's the principle? Because in statistical learning, we know there's this universal, the likelihood principle that says, we want to minimize the KL divergence between our model and the data, right? We want to find the model that minimizes the estimated KL divergence. And maybe we have prior beliefs and we penalize that. But for causal models, I want to know what the principle is there. And maybe, because it's more than, it's not just how well we fit the data, because we have to take into account of these interventions and the potential confounders and how we reason about those. So I don't know what the corresponding principle is there. I believe that Elias Barenboim is working on a paper on this, so I think he's likely to give a good answer because he's really smart and just does wonderful work in this area. So I think we all want to somehow understand how we can generalize in a kind of a non-statistical way, right? Or how we can understand, right, what are the invariant factors at work and what are the stochastic or the just random confusing, unimportant confusing things. And so, I like this invariant risk minimization paper that Leon Batu and Aryovsky had last year. I think it's kind of confused, we don't.
I think he also gave like parts of it as light layer.
Yeah, he's good, right, yeah. And so there's something right about that, about looking for invariance, but I think it's still not, I'm not sure that you can actually optimize the objective they give in that paper, so I think there's some bugs. But things like that I think are really interesting. Like, in general, the problem is, if we have knowledge about what we think are the invariants, we should be able to communicate that to our systems somehow, either by data, by experiments, by telling them, by giving a constraint space of hypotheses. I don't know what it would be, but we need to get that in there because right now they're they're picking up on these kind of very accidental features that happen to have predictive power in our data sets, but not in the real world, and it's making big mistakes.
So the last question I have before opening the floor for any other questions is, I think, we are almost closing. So public perception of AI, this is something that you spend a lot of time on Twitter. I think we're all stuck between people over imagining the AI's capabilities, but also there are people who are sort of underselling what actually I can do. And I think you actually wrote this very nice medium piece trying to argue that we should take credit for certain things that are working, instead of just saying, only complaining about why not everything is working and so on. So I was sort of wondering, actually I would like to kind of maybe state your position on that. I think for the students it will be very useful because you spend a lot of time thinking about these sort of things.
Well, so probably many of you are familiar with this. I can't remember what it's called, the AI phenomena or whatever that. In the history of AI, we would master some capability, and then people would say, "Oh, that turned out to be easy," and that wasn't real AI.
Yeah.
And so AI was always defined as the stuff we haven't figured out how to solve yet. So it's always like this residual category. It's kind of like non-linear optimization. It's everything that isn't linear. But and I think it's partly because the term AI is still like this repository for all these romantic ideas that come from Hollywood or from the deep past. All through at least Western civilization, there are all these, there's the golem in sort of Jewish history of this thing that becomes sentient even though it's not human, and also there's the Pinocchio story. I always joke there's really only two stories in these Hollywood plays. Or movies. There's either the Pinocchio story, which is Commander Data also wanting to have real emotions, or there's the Terminator, and that's like the two faces of AI. And those tell us more about humans than they do about AI, right?
Yeah.
What is special about us, and also what do we most fear about ourselves? So I want to fight against this tendency to say, well, that these accomplishments that we have, I think Google Translate is amazing. It's certainly not perfect, and it doesn't reflect very deep understanding, but it's amazing. And of course, human translators don't necessarily have very deep understanding either, and they're absolutely critical. So I think we should celebrate our successes, I guess.
So actually there was this one other highly rated question that I forgot to ask you, I guess, which is a very probably anticipated and too, which is, what would be your advice to PhD students starting research in AI? I'm sure you mentioned a bunch of them already. Of course, they all should get the old version of Do Down Heart and read tonight. So what would you say?
Well, my generic advice to my PhD students is you cannot know too much mathematics.
Okay.
So I encourage my students to take, functional analysis, convex optimization, theory of statistics. I think that, right now, knowledge representation is out of favor, but I think you should know your logic and stats, at least Davis-Putnam, but you should know about CSPs and these other reasoning technologies that we have that are very powerful. And I think you should know about probabilistic modeling and probabilistic inference. So understanding variational models and some of these Monte Carlo techniques, at least, understand the sort of strengths and weaknesses of Monte Carlo techniques. So my favorite probabilistic programming language is Stan.
Stan, yeah.
So I think it's really amazing that they've managed. It's a restricted language, but they've made it usable by a huge community. It's just had I was on this DARPA program where they were all struggling, and out over there, the Stan guys are like have 10,000 users, and it's like, okay, what's wrong with this picture? So I think that understanding the power of probabilistic modeling, I think is really good. What else? But those are all like component skills. Now, in terms of then the question is, well, what should you study as a PhD thesis? And the trouble is there, you have to think about something that's doable in like 1 year full-time effort or something, right? I mean, Don Knuth had this advice, right, about you should solve a series of problems as a graduate student. One that takes a minute, and then one that takes 10 minutes, and one that takes an hour, and one that takes a day, one that takes a week, one that takes a month, one that takes a year, and you're done. And I think that's probably good advice. But the thing is, so I don't know what the feasible things are. I mean, this is where you have to talk to your advisor and think about it. I mean, I'm placing my bets on autoencoders and generative models for anomaly detection. So I'm working on anomaly detection in images, anomaly detection in, say, control for robots from, say, image feedback or image sensing in open worlds. I think there's lots of things doable there. I have just discovered that I need to be interested in domain adaptation. So I think a very interesting area is, break one assumption in the machine learning formulation, like closed world, closed feature set, batch versus online, non-stationarity, or robustness and adversarial. But don't try to break two of them at once, maybe, if you want to graduate. But I think, another piece of advice that I got was given was, after you finish your PhD, well, his first thing is that he would always tell us, the first job of a graduate student is to graduate. Get famous on a higher salary. So know that your PhD thesis is not going to be the basis of your reputation in your career. I never published anything based on my thesis because it was so bad. But it was a good training experience, and that's basically what it is. So, but then he said, think about your career in as say 3 or 4 10-year chunks, and be ambitious about those things. I mean, if you look at the people that are on the National Academy, they're on there because they did something that was more than a 2 or 3 year project. They thought about something big, and they then figured out how to get the resources and build the organization to make it happen. And some people get there because they wrote the #1 textbook in the field. And that's great too. That's another one is the scholar. That's probably also 10 years. I don't know. Especially because you have to keep revising it there too. But I think it turns out that publishing papers is actually not that hard to do. And you can kind of master the paper publishing thing if you like least publishable units and get lots of conference papers. But it's rare that that's really going to move the field in a significant direction, unless it's part of a larger effort that's going to result in, another Ed Feigenbaum rule was, at the end of every project, write a book with your lessons learned. Which I've never managed to do. I tried to do one on Kalo, and I got like 80% of the way done. But then too many other things happened. But they wrote a book on mice, and they wrote a book on Dendril. They wrote a book on blackboard architectures. So yeah, you should start planning your book on human aware AI and what should be in it.
Do that. I'm sorry.
Well, and yeah, the way to do it is to have one graduate student per chapter.
Yeah, exactly.
Basically,
Some more than
perceive or short summaries of the main things you learned from the different.
So, is there anything else that you wish I had asked? I mean, this has been fascinating to me, and I hope to the students too. Is there anything else that you wanted to share with us?
Well, I guess, I mean, I think we, as a field, we need to think much more now about our broader impact. So you asked a question I don't think I really answered, but I feel that very often in AI has made progress by importing ideas from other fields. And for machine learning, we sort of swallowed statistics whole, or at least large parts of it, along with optimization. And of course, we had our unique spin on that, but it's been extremely productive. And we're planning an OR, right? So we should realize that the intellectual space is kind of different from the departmental space and the dissertation space. And so now I think we're all seeing, we need much more cognitive psychologists, anthropologists, philosophers, and ethicists, because our systems, when we deploy them, are changing the world. I mean, here we are talking about, at least in machine learning, IID, probabilistic models, and yet why would you be building a predictive model if you didn't hope that it would be used? And if it's going to be used, it's going to change people's behavior. And so it's guaranteed to change the distribution. So we need to look at that feedback loop. And basically, we are misspecifying the whole situation by treating it as IID. And so we, and I think the same thing with advertising, right? People formulated it as a multi-arm bandit problem, one shot, and didn't think about the fact it's really like an RL or a game, or so we need to really broaden our horizons and ask, especially because a lot of the system is going to be people and human behavior, and how does that feedback and affect us, and how are we affecting them, and what kinds of changes are we creating in the world, and I love this DARPA program that was called BRASS, I think, a few years ago, that raised the challenge, how could you keep a piece of software working for 100 years? It was aimed at sort of software engineering. But they said, the libraries are shifting, the computers are shifting, everything's changing. How can this system survive for 100 years doing basically what it's supposed to do? Well, the AI version of that, I think, is imagine building an autonomous AI system that could do what you want it to do for 100 years. That could outlive you and still be obeying your values and so on. How would you program such a thing? You can't do it by saying, well, I like this behavior and I don't like that behavior. That's way too low level. I think you have to program with a level of ethics. And the trouble is ethical principles conflict. Okay, and so you also have to teach the system how to resolve conflicts in your ethical principles somehow. I don't know how to do this, but I feel like that we, AI has often also made progress by raising the level of programming, first up to lists, and then up to things like plans and goals and beliefs, and now I think we need to move up to these larger things about ethics, and we have to realize that a lot of ethics is also about communication in society and social relationships. One of the most important things I learned on Twitter was one of the ethicists posted a thing about how trust is more than predictable, reliable behavior. And I said, it is? I thought that's what we're doing, trying to make AI systems predictable and reliable. And so I went up to this resource, the Stanford Dictionary of Philosophy, or encyclopedia. Fantastic resource. Yeah. And I looked into the paper and the section on trust. Oh man, it was all about the fact that there are performative aspects to trust. If I trust Rao, I am making myself vulnerable to him.
Exactly.
And also he now has an obligation to me that if he cannot carry out my wishes, he better get back to me and tell me about that. Okay, whoa, this is a lot more complicated than that he's, in fact, he might not be very predictable, but I think he's trustworthy just the same, right? Oh, it just blew my mind. Okay, so I feel like this is we need to think much more about these kinds of things.
So it's actually quite fascinating that when I was a grad student, and probably obviously you over time too. AI used to be quite interdisciplinary from a technical side. Now we are again becoming interdisciplinary because of the applications and how they're going to impact the world. And so the trust, the human factors, and psychology, they're all coming back. So that's kind of one more of the answers that, it's not just a narrow view.
Which means we all have to collaborate, because
Exactly, yeah.
you can't learn everything yourself.
So this has been really fascinating. I didn't know how this would work, but you're amazing. Thank you. So,
Let's see. I'm going to go see Steph, or she's going to come see me.
at 5:50.
Great. I already did my